Yeah, I will stop. Okay.
Is it visible?
Yes, it's visible. Go ahead, boss.
Well, thank you, Tunde, and thank you to all the organizers for the invitation. Really happy to be here a second time around. I've really enjoyed listening to the fantastic talks so far, the ones I've managed to attend. I'm actually not in Buffalo. I'm in Jodhpur in the middle of the Thar Desert at Indian Institute of Technology here. And I'm on leave. I'm on sabbatical leave for several months. So I've been unfortunately quite occupied, which is one reason why I'm guilty of not having attended every session like I did last time. So I'll talk about something which is a little different from probably most of the conversations that have taken place so far in this Nonlinear Physics Group conference. I'll talk about frequency and amplitude attenuation using decorated granular metamaterials. So this work's been done by Professor Luis Machado. Luis was my former postdoc. Unfortunately, he is unable to actually present because he is on vacation in Rio. And so I've been tasked with presenting it. But of course, Tunde invited me. But anyway, so I'm not that guilty. So basically, let me move this window on my screen a little bit. So basically, what I'm going to talk about is how do we deal with frequency and amplitude attenuation of sound? Okay. Now, the reason why this problem attracted my attention some time ago is because if you look at the numbers, about 500 million people in the world is hearing impaired. And this data is as of 5 or 6 years ago. Now, 500 million people out of 7.8 billion or 8 billion is a big number, right? But it's worse. It's getting worse. So by 2050, which is very much in the horizon now, we are looking at a number which is close to a billion people. And it's also true, apparently, that approximately 90% of people with moderate to profound hearing will actually be residing in the poorer countries, lower and middle income countries. And therefore, this is taken as a very serious health issue by the World Health Organization and many other groups. So this is what attracted my attention to looking into ways to make systems as sound absorbing as possible. Now you can say there are soft materials and so on. Yes, most of them are plastic materials or fibrous materials. Many of them are not the most sustainable materials, nor can they be easily 3D printed and so on and so forth, nor can they be miniaturized and so on and so forth. So there are advantages to various materials one might choose, and granular materials therefore have their own potential advantages. So that's the reason why we decided to look at granular materials. Now, this is one of my boilerplate slides because I've previously spoken on granular materials here and elsewhere many times. So in granular materials, like you have in the Newton's pendulum on the top right, you have Hertz law at play. So as the grains compress each other, the repulsive force between the grains builds up rapidly. This is the Hertz force. And this Hertz force is given here by the Hertz law. And you can see it's an intrinsically nonlinear law. There is no linear term at all. And this coupling A turns out to be important. It includes the two Young's moduli of the two spheres in this case, if they were to be different. And many years ago, Vitaly Nesterenko used to be from Novosibirsk. Vitaly has been a professor at University of California at San Diego for many years, since mid-90s. Vitaly had showed that if you take an alignment of grains, like here, like in this tube, and if you put an impulse, in this case on the right side, you will actually see a solitary wave that goes through the system, and that will be recorded in this pressure gauge on the left in this experimental picture. So in other words, granular alignments transmit solitary waves. So therefore, granular alignments have been of strong interest to people for a long time. The equation of motion that one can use would be this kind of an equation of motion. This big delta here, that's like a preloading. So if you go back to our previous system out here, if these grains were to be pre-compressed, in this case, they're not, as you can see, they're touching each other. But if they were to be pre-compressed, then that would be manifested through a non-zero value of this delta. So it's a non-perturbative system here. And one can show that this kind of a system actually transmits a solitary wave pulse, which is about roughly about 3 to 5 grain diameters wide. Why are they as wide as they are? Well, the reason basically is that here, for example, if you look at this potential V of delta versus delta, delta is basically overlap, which means how close the grain centers are to each other. That's what delta means. The dashed line is a quadratic curve, and this 2/3 curve, or 5/2 in this case, actually, for the potential, is the blue line. And you can see that this blue line grows more steeply than the quadratic curve. If a potential grows more steeply, that means it becomes energetically more expensive for the grains to remain in contact, which means the grains would like to break their contact, which basically means that the energy is transmitted in a bundle. That's what it boils down to. So this is my intuitive explanation as to why solitary waves might be expected here. And in this picture, the top left is the case that we are dealing with, where you can see that the pre-compression, this delta that I alluded to, is 0, and you're getting one solitary wave here. There are some other small solitary waves. I will not talk about it. I've talked about it earlier, I think, last year when I spoke. And then if they remain pre-compressed, it turns out that there is some there's an oscillatory tail that tags along. Again, that is not very important for us right now. So moving on, Vitaly showed a couple of things. One of the things he eventually, one of the things he first pointed out was that the equation of motion for strong compression likely is a KdV-like equation or a KdV equation. It turned out that was not true. It turned out, yes, you may be able to reduce it to a KdV equation, but it does not behave like a KdV equation, meaning there was something complex about the way the real system works. So he later went back and tried to make delta, this pre-compression, quite weak. And it turns out that gave the equation in the red box that turned out to be more or less correct, approximate, but more or less correct. And that gave Nesterenko's famous solution, for which obviously he's very happy, as you can see. But the bottom line is that the solitary wave solution can be seen, but only in the weak pre-compression or strong nonlinearity limit. So let me now come to another system, which is a tapered system, tapered chain. You can look at any one of these chains. If I were you, I would look at, for example, the bottom right picture, where you have this granular chain with interstitial grains. You don't have to have the interstitial grains. They actually make a system more energy dispersive, not surprisingly. But suppose you remove these interstitial grains, it becomes a simple tapered chain, where the tapering is defined by this Q of D, Q sub D. Basically, Q sub D is by how much the grains shrink, the grain radii shrink. And it turns out that if you look at any of these diagrams that are put up, K sub N is the kinetic energy of the last particle, which in this case would be the extreme left particle. So essentially, the kinetic energy of the last particle is severely degraded with respect to the initial kinetic energy when the number of grains goes up. In this case, you can see at around 20. And when the tapering goes up, in this case, we have studied tapering until 0.1. Now, this system is not really analytically solvable, but if you make it a hard sphere, it's very easily solvable. And those solutions are given in this paper and many other papers by others. We introduced this system a long time ago. As you can see, we called it the decorated tapered chain. So the tapered chain and the decorated tapered chain systems have turned out to be pretty well accepted and used impact absorption systems in many devices. So moving on, we did a number of different studies with the goal of getting back to the original problem, which is designing systems that are amplitude and frequency attenuators. Now, it turns out there is no easy formula, at least as far as we could tell, for findings of systems. So we initially studied with two sets of systems. As you can see on the top, A1, B1, and C1, the pictures I show. We initially examined what happens in terms of simple transmission of an impulse of a system of grains with same size, a tapered system. As you can see, these systems don't have any wall on the right. And then you have a system where you actually have interstitial grains, but otherwise a monodispersed chain. And these interstitial grains are kind of interesting because we have made them fixed on the wall. So what that really means is that these grains can get squeezed. These small dark grains can get squeezed, but they don't carry kinetic energy. That's what it means. So in other words, they're welded tightly, such that as say kinetic energy propagates from k equal to 1 to k equal to 2, this little guy here plays the role of impeding this transference of energy quite a bit. So that's one system we studied. Now, the impulse system is actually not all that interesting. It's not uninteresting, but it's not interesting enough. What is more interesting turns out to be the case when you actually drive on the left side in a sinusoidal manner. And you can vary the frequency, you can vary the amplitude, and so on. So this is really where we're getting into the nitty and gritty of the sound. So these systems turn out to be notoriously difficult to study, something that we had observed back in the early 2000s and wrote some papers on it, but nobody paid attention because this seemed very odd. It turns out that they have some interesting applications, and the applications sit in the domain of sound absorption and so on and so forth. So we studied these three systems. First is the monodispersed chain, second is the tapered chain, and third is the same system as in C1 above in red circle, but now you have these frozen interstitial grains. In other words, this extra factor that can make it much more energy, much more hesitant to transfer energy easily. So with that, let me move on, if I can. Okay. So this is the equation of motion, where essentially this is the way to write the compression of the grains as they squeeze against each other. The initial velocities in the perturbations we took are not very large, but they are not very small either. At 30 meters per second, the system still remains quite elastic in terms of being able to use Hertz law. And in all these systems, there is always some kind of restitutive loss because these are macroscopic systems. The restitutive loss is often not huge, but it's there. And one way of modeling it is by taking the ratio of the unloading over the loading force and writing it as 1 minus W, and then W is a small number, typically 0.1, 0.05, something like that, much less than 1. Moving on, here is a study in which we have taken the C1 system. C1 system was the one in which you have the grains, and then you have these frozen beads, but the beads are compressible. And we tried out what kind of materials for the larger grain and the smaller grain turn out to give us the best possible couplings. So here are 9 cases of material combinations to be studied. The materials that provide the largest value, let me see if I can get it. Largest value of A, this quantity A here, turn out to be the better materials in this case. So that would basically mean the largest numbers when you take 2 of the materials. For example, you can take tungsten here and delrin, which is like plastic here. And it turns out that is the best one with the largest value of Y star. In this case, it basically gives you an impedance mismatch. That's really what it does. But anyway, we had to find it by trial and error. Another thing that we had to do was we also had to pick out what kind of radius of this small guy you need and what kind of radius of this large guy you need. Turns out to be about 0.2 is the best, but then it's not easy really to determine that, because at least we don't know of any obvious simple theoretical ways to figure it out. We worked on it, we couldn't figure it out. So here you can see the momentum of the striker versus that of the particle at the other end, the last particle, number of grains in the chain, and the small r over big R. Again, to remind you, this is small r, this is small r, this is big R. And it turns out, as you can see, that the momentum attenuation is the largest, just around here, 0.2. And this is the two-dimensional picture, so around 0.2. And it is indeed for Delrin sorry, Delrin is the big particle, and tungsten is the small fixed particle. So I said it wrong. My apologies. So anyway, moving on. If you, so this was an impulse problem, obviously, from the left side. But if you actually now turn on the actuator and keep driving this sinusoidally, then you can ask the question as to what happens on the right side. So this is the case when you have a monodispersed chain, and this is the case when you have a tapered chain. On the other end, there is a rigid wall, by the way. That was not the case in these studies. As you can see, it was an open system, so the last particle could pop out. And so it was easy to measure the momentum. So it was a one-shot deal because we are studying an impulse. This, on the other hand, we are not studying an impulse, we are studying an actuator. And here we can ask the question as to how will this actuator transmit the various frequencies and various amplitudes for this XACT, the driver. It turns out that the frequencies that it would transmit or not transmit are on the y-axis, and the actuator amplitude are on the x-axis. As you can see, we have taken the monodispersed chain we have taken, which is without any dispersion, any restitutive loss. So this is W equal to 0, W equal to 0.1. We have also taken some tapered chain systems with small w values, and it turns out that they tend to transmit the vibrations pretty okay at low enough frequencies, but they don't like to transmit the vibrations at high enough frequencies. So you can see, for example, if you have a tapered chain out here, then you really at small amplitudes, you're transmitting up to about 400 hertz. If you raise your amplitude, you might get up to 600 hertz, 650 hertz, but no more. You won't be able to go further up. The systems have natural frequency cutoffs, and that's partly because of the way the Hertz force works and the ability of the trailing grains, meaning the grains that are further down, to follow the first grain. So it can't really keep up with the vibrations of the first grain. It tends to slow down, and physically that's the reason why these cutoffs come. But the exact values of the cutoffs we are not able to analytically reduce. One comment I would make is we have these are extremely time-intensive and highly accurate simulations. We have actually looked at systems where if instead of spheres you took disks, so that would actually give you, instead of Hertz law, a harmonic law between the grains. What differences would arise in that case? It turns out that there are some differences, but they're not as dramatic as I thought they might be. So we wrote a paper on that. I'm not talking about that. I just wanted to mention it. Now, moving on, it turns out that all these systems actually have some high frequency cutoffs, as I said. And if you look into the dynamics at the microscopic scale, just like I said, this is the dynamics of the fifth grain, and this is displacement, this is time. And this is the dynamics of the actuator part. And you can see that the fifth grain's dynamics is very, very different from that of the actuator part. It's much less in displacement. This is much higher. We're talking a number which is way above 2. This is like 0.3 or something. And this also attenuates. And eventually the system can't keep track of it. And by this time already, you are getting into a cutoff if you're looking at the gain factor, where the gain factor is essentially a ratio of the output amplitude and the input amplitude in this formula, this is a standard formula. So moving on, if you turn on the tapering as we have, if you have the W value here, and in this case, n is 5, so it's a small, very, very small system, which means it's super tiny. You can 3D print it out very easily. You are really talking about a system where you have a transmission region that again gets around 600 to 800 hertz, depending upon the amplitude. But above that, it works as a very, very high quality sound filter. Moving on, if you take this system, which is tapered without interstitial grains, versus this system, which is not tapered, which is actually a soliton transmitter, but now with this interstitial frozen grains, this is the kind of phase diagram that you end up with after a lot of work. And if you look at the numbers here, it basically means the entire system has become an acoustic insulator. It doesn't literally transmit any measurable amount of sound just by putting in the interstitial grains. So it turned out that this interstitial grain strategy was very successful for us. Another system that we looked at over several papers was this granular crystal, if you will. This is a relatively straightforward crystal. Everything is monodispersed with interstitial grains. On the right, we have a somewhat more funky system where you actually have tapered chain type structures, which are natural impact dispersion systems, along with inverted tapered chain black structures. Not quite an inverted tapered chain, but like it, because they're not in contact directly. So if you look at this system, it turns out this has actually somewhat improved properties of signal dispersion than even this one that I showed you. But before I go there, let me point out that even if you take a 2-grain system, just 2-particle system, even that is a very good sound absorber or sound dispersion device. So this is actually a 2-particle system. And here you have the region where the signals are transmitted at low amplitudes and low frequencies. The dynamics can be quite chaotic, but at higher amplitudes, it is very good. You're looking at 3 to about 7 or 8 kilohertz. In this region, this is the input at the left end, or the bottom here. This is the output at the right end. And it's okay. This is, of course, transmitting it. As you would expect, it should be more or less the same. On the top here, on the other hand, when you enter the filtered region, this is the input and this is the output. So input is here, output is there. And even a 2-particle system cuts out the higher frequencies, which is not a surprise, because if you drive this grain, the grain on the top here is much more constrained. It tries to follow it, which is the case here, can't follow it after a time when the motion builds up and the compressions build up, and ultimately its motion really slows down. There's a natural retardation that happens. This system becomes quite interesting when you actually see a slightly bigger system. In this case, you have a real 2-dimensional system with the same kind of architecture, in fact, a little bit more sophisticated, with the tapered chain and the inverted tapered chain staggered with one another. You are driving sinusoidally from the left, and here you can see that there is some level of signal transmission in the lower frequency, and there is a very significant cutoff signal filtering. At the higher frequency regime. So again, this is quite an improvement on the things that we have done in terms of how things are transmitted. Coming to the last system, I want to tell you, this is a paper that we have just submitted, where we took an even simpler system, where we took the tapered chain system, but in this case, the small particle is being driven instead of the large particle being driven, which is the case we have traditionally studied when we first introduced it in 2001. And the literature essentially has studied it as an impact dispersion system, in this case, going from right to left. That's how the literature has done it. That's how we began it. But now, what if we reverse it? What if we just drive the small grain? Now, as you can see, it's a bit of an uphill climb for the energy to move to the right, because it has to go through larger and larger particles. That in itself creates a strong inertial mismatch. Not to mention what happens when you drive it. Not to mention what materials you want, because that also fixes the couplings. So we chose a very light material. This is the nickel titanium material, and Teflon, which is very easy to find. Came out of NASA, as you know, probably. So anyway, the nickel titanium and Teflon combination system turned out to be very good. And I will not take you through the big detail unless you're deeply interested. But this is the kind of stuff that you get in this system. Quite interestingly, at low frequency and across interesting amplitudes, you actually get a transmission region. So the signal transmission is quite good. But then you have an amplification region. You have a region where the signal is actually amplified, which was a surprise for us. But it turns out that in this system, because of that mismatch and the geometry I showed you, this geometry that I showed you, there are a bunch of particles here, a bunch of particles here. This 3 is an interesting number because remember I mentioned that the solitary waves are 3 particles wide. So whenever you put in 3 or 4 grains, there tends to be a little bit of a solitary wave-like propagation, although this is not monodispersed, but still the tendency remains. So that was the reason why we chose these 3 grain clusters. So it turns out that anyway, there's this amplification region, and then there is a strong filtering region where the impact transmission, where the sound transmission goes away. But this amplification region is quite extraordinary. We didn't expect it to become a sound amplifier. So summing it up, if you have a noisy system like here, you go back to Nesterenko's transmission system, you go back to the impact decimation system, you play with it, and you can essentially come up by trial and error largely with a variety of ways in which you can design pretty good quality impact absorption devices. Thank you very much.
Thank you so much. Right, you have a question. Is my understanding correct that in all the cases you consider here, the system is pre-compressed?
It is not pre-compressed. So the grains barely touch each other. If you pre-compress it, God knows what will happen.
I see. So without pre-compression, I'm just wondering how would you be able to get this in the monoatomic chain? How would you be able to get this transmission band and forbidden band? Because the equation will be just nonlinear terms, right?
So if I understand your question correctly, you are saying why should there be this kind of geometries where the amplitude and frequency wouldn't transmit? Is that what you're asking?
Yeah. So if my understanding correct, I think the equation without pre-compression, I think the equation will be only this delta plus power 3/2, and we cannot do linearization, so there is no transmission band and forbidden band in that sense.
Correct. You're absolutely right. So if you have a single monodispersed chain, all you'll do is put the solitary wave through. But even if you have a monodispersed chain that I have here in figure B1, suppose you are not even driving it, you put an impulse in, even then you wouldn't be actually having a solitary wave transmission. Your transmission would be severely altered because this is actually no longer a purely one-dimensional system. The energy will go from here to here, here to here and lose some because it will squeeze it. And then it will come here and the energy will also go from here to here. So if you observe, they have been designed in such a way that there are many touch points. There's a touch point here, there's a touch point here, there's a touch point here, and here and here. So that's intentional. That's to keep it such that we don't pre-compress. That's one point I wanted to mention. Second point I wanted to mention is the reason why these dead zones, so to speak. So in other words, the amplitude and the frequency don't go through. Why that happens is because you can have very easily a scenario where a grain is moving like this. This grain is, has a different neighborhood. Its frequency may be higher or lower. And so all kinds of possibilities might happen. And you can easily see that the oscillations of the first grain can essentially kill off whatever is happening here. Or it may be very small amplitude, very high frequency, and that small amplitude might die off. So those are the kind of things that we had to look for, and hence design the system in such a way and play around that you can precipitate those kind of dynamics that you would like. So in other words, they're strongly phase mismatched and strongly amplitude mismatched by sheer design in this case. The fact that sheer design can give you this was not expected. At least I didn't expect it when we started first playing with it. So obviously, when you have a coupling mismatch, when you have size mismatch, when you have boundary conditions, and when you have driving, God only knows what happens. That's the best I can say. I hope I've answered your question.
Yes, thank you. Do we have any other question? Okay.
Thank you.
Well, with all this, I got the privilege to close this wonderful international event at UAE University. I would like to thank all the speakers, online and in person. Thank you so much. We did it this year in person. Last year we were online, we remember. So hoping for the best for the coming years. And of course, in the end, last but not least, the big man, the one-man show. I think I would like to thank all the physics department who organized, who invited us for this wonderful event, the organizing committee, and one man who deserves a big clap. Who is this? Tunde, please. So, yeah, thank you so much, Tunde.